Better indications are the voltage and current meter readings on the battery charger. When the cells first start to recharge, both voltage and current are relatively high. As the cells approach full charge, the voltage gradually increases and then stabilizes, while the current gradually decreases and then stabilizes. The cell and battery ratings covered in this part of the program are the traditional indicators of a battery's ability to provide backup power. If you understand the relationship of cell voltage, capacity, and specific gravity, you can compare rated values with measured values to determine whether a cell or a battery is good, marginal, or bad. A battery charger serves several functions in a typical battery system. First, it converts an alternating current input into a direct current output. Second, the charger applies the direct current output to a battery and controls the output in order to keep the battery fully charged. The charger may also provide some or all of the direct current to the DC load. The battery supplies the DC load only when the load exceeds the capacity of the charger, or when a power outage prevents the charger from providing direct current to the load. Chargers can vary in size and design, but most have some common components or features. An AC breaker is provided for connecting the charger to or disconnecting the charger from its source of alternating current. A DC breaker is provided for connecting the charger to or disconnecting it from its DC loads, which include the battery. A DC voltmeter indicates the charger output voltage being supplied to the DC loads. Normal voltage in this system is usually a little above mid-scale. And a DC ammeter indicates the charger output current. A battery charger will also typically have a switch or timer that is known as a float equalize switch. The terms float and equalize refer to two different charge voltage levels that may be applied to the battery. When the timer is off or at zero, the charger operates at a normal preset float voltage. When the timer is activated, the charger operates at a predetermined higher equalize voltage for the number of hours for which the timer is set. After the time elapses, chargers with a timer automatically return to the float charge voltage. Chargers with a switch must be manually switched to the float charge mode. In addition to the float equalize switch or timer, a potentiometer is provided for adjusting the float charge voltage. And another potentiometer is provided for adjusting the equalized charge voltage. In addition to all the components just shown, a charger may have a number of other components. Some chargers may have a pilot light. The light is typically on when there is an AC input to the charger. A charger may also have a ground fault detection system. The system on this charger uses positive and negative ground fault indicating lights. Both lights are typically dimly lit. If the positive side of the DC system becomes grounded, the positive light will glow brightly and the negative light will go out. If the negative side of the DC system becomes grounded, the negative light will glow brightly and the positive light will go out. This charger also has positive and negative ground test buttons. Each button, when pressed, will introduce a ground in its respective part of the system. The buttons may be used to check that the ground fault detection system and lights are functioning properly. Finally, a charger may contain a variety of alarms and relays, including a high voltage alarm and relay, a low voltage alarm and relay, and a power failure alarm and relay. The specific components can vary from one charger to another, so it's good to learn which components are included on the chargers in your system. In this topic, we looked at a typical battery system. We covered the components of a lead-acid cell and described the electromechanical actions that occur when a cell is charging and discharging. We discussed cell and battery ratings, including voltage, capacity, and specific gravity. Safety is a serious matter. Electrical shocks and acid burns can be severe if the proper precautions are not taken. And the loss of eyesight is a very real possibility if the eyes are not properly protected. All required safe working practices should be followed to the letter. For example, before beginning your work, remove all metal objects, including rings, metal watch bands, metal necklaces, dangling keys, and any other personal items that could cause a short. Even a single cell, if directly shorted, can melt a ring on a finger. Protective equipment should be worn, including a long-sleeved shirt, an acid-resistant apron, insulated acid-resistant gloves, safety glasses or goggles, a hard hat, and a face shield. Some companies also require the use of acid-resistant sleeve protectors and rubber-soled shoes or a rubber mat on the floor. Also, you must know where the eye wash station is located before you begin working, so you won't have to search for it if you need it. And if you're not familiar with the eye wash station, read the treatment procedures before you start work, so that you know how to use it if you need it. If you need to use tools on the battery, they must be non-conductive, have insulated handles, or have all metal handles covered with a protective material. Only after you have taken the required safety precautions is it okay to begin work. Here is what a good fully charged lead-acid cell looks like. The electrolyte level is between the high and low level marks on the cell jar. The negative plates are thin and are a gray color, and the positive plates are thicker than the negative plates and are black or a dark brown color. One common cell problem is low electrolyte levels. Low levels are often caused by the small currents needed to keep the cell fully charged. The current changes water in the electrolyte to hydrogen and oxygen gases that leave the cell through the vent or the flame arrestor. Over time, a certain amount of water is lost. In general, lead antimony cells lose water faster than lead calcium cells. If the electrolyte level is low, water should be added to raise the level so that it's between the marks. Only distilled, deionized, or other approved water should be added. Tap water should not be used because it contains impurities, contaminants, or minerals that can shorten the life of the cell. Each cell is also closely checked for problems such as sulfation, cracked plates or plate growth, and hydration. If the electrolyte level drops below the top of the plates, sulfation can occur. Sulfation is the hardening of sulfur deposits on the plates. The deposits can prevent the cell from taking a full charge or from delivering its rated output current. Sulfation also occurs during the normal discharge of a cell. When light is shined on the dark positive plates, the sulfur deposits reflect the light, like sparkly glitter. Generally, the deposits are driven off the plates as the cell is charged. However, if the cell isn't maintained at full charge, the deposits will grow and become more difficult to reduce with normal charging. Another undesirable cell condition is a high electrolyte level. A high level may be produced by excessive gas in the electrolyte that forms from overcharging a cell. A cell that's undercharged will show different symptoms. It will have positive plates that are light brown or tan. If the cell were fully charged, the positive plates would be dark brown or black. Yet another undesirable cell condition is plate growth. Essentially, plate growth is the swelling of the grids. It is caused by grid corrosion. Corrosion results from the long-term effects of the sulfuric acid in the electrolyte on the grid. Plate growth can distort the plates, cause the grids and lead to break up, and prevent current flow through the cell. It may also cause the cell jar to bulge. In addition, plate growth will often push the terminal posts up, breaking the seals at the posts and allowing electrolyte to leak out of the cell. Finally, a cell may show a horizontal ring of white deposits around the plates and on the inside wall of the jar. These deposits are the results of hydration. Hydration is the dissolving of lead from the plates into the water in the electrolyte. Hydration occurs when a cell remains completely discharged for a period of days. The dissolved lead and water compounds, referred to as lead hydrates, crystallize and settle on all parts of the cell. Lead hydrates in the separators provide thousands of short-circuit paths between the positive and negative plates. The